Be strong.
Lastly, they do not tell you, okay, we tried this 5 times and only 1 time it worked. No paper will discuss that, right? They will only tell you, okay, we have done this is the data, etc. Sometimes we even change our hypothesis based on reactions because we want to publish the paper, right? So it is very seldom they will tell you negative results. Yeah? But that doesn't mean that when you do it, you will not get negative results. Sometimes even those procedure which is published, when you try to repeat in the lab, first time may not work. That may be because your solvent is not pure or your reagent is not the same. There may be multiple reasons for it. Or the paper will the paper will say it has 90% yield, but when you do it, you may get 20% yield. Yeah. Again, that is not because the people reported is made a mistake. It's just that you are just doing the first time. And the people publish, they might have done this for almost a year, because it takes a year to get these things results compiled and publish those things, right? So they have done this many times, so they optimized it, they get a better output. You are just doing first time, so therefore you have that. So in that scenario, you should analyze. Yeah. Again, I've seen many times that students who conduct an experiment today, collect a spectra, go home, and then never look at it, right? They made an immediate assessment, oh, it did not work. But they do not ask a question that why it did not work, what went wrong, how it happened. So that is the kind of things you need to do when you are learning about the experiment. Yeah? If you don't ask those questions, tomorrow you come and redo the same thing and you get the same results, because you have not learned anything from that particular experiment. So you keep on wasting your time. In fact, long time ago, I had a student who repeated the same reaction 9 times, and 9 times he had the same results. And then I was wondering, what is happening. So I just started asking questions, blah blah blah. Eventually, I found out that he just repeats the same thing over and over again. He doesn't really think about it. But these are, it's not unusual. It happens in our life, right? Because sometimes we just rely on the paper, reference we have, and then we keep doing, hoping that it works in your hand. But unless you understand, it will not work. Yeah? When you try to repeat the same thing over and over again, there's no chance it to go make it work. But if you have one reaction, if you do it, analyze it, and then learn from it, of course, next time when you do it, you will improve it. You can change a little bit here and there. For example, you did a 50 degrees, you may think that, oh, no reaction, let's do it at 80 degrees. Yeah, that is possible. Or if we say, oh, the catalyst was bad, old one, let's change the catalyst. Those are steps you can do. Yeah? Only when you make those kind of decisions through a learning process, your results will be better. Otherwise, you get the same results as yesterday, right? So that's what it means, observation and learning process. And these are all part of the research you do on a daily basis. It's not unusual you do it only 1 time a year. No, every day it happens like that, right? And it also happens in our life. I mean, these are not unusual things we are talking about, right? So for example, if I go to a restaurant, I do not know what they cook, or especially if you go to I still remember my first trip to Japan. And I did not know what kind of food I was going to get there, right? So I don't know whether you guys now I like Japanese food very much, sushi or sashimi, etc., right? But first time when I was eating, it was very difficult, because in India we don't eat raw meat or raw fish very often, right? Because weather is very hot and it gets spoiled very fast. So, but in Japan it's a very different story, right? So when you have the background where you eat everything cooked, but you are given a raw one, it's hard first. Yeah? But these are things you learn. Now if I go, I have absolutely no problem. In fact, even in Singapore, we go sometime to Japanese restaurant, right? So that your learning process, your experience all come to practice. Yeah. So that's what I'd like you to do in your research as well. Where maybe you first time when you do it, it will be very difficult to go through the entire process. Yeah, you might not understand. But then take a step back and read and understand, right? And then second time will be much better. Yeah. So please don't just do mechanically. Then you're kind of doomed, right? You repeat the same mistake over and over again. Sometimes you get into trouble as well. Okay. Preparation work. So when you do the experiment, you need a lot of things to do, right? The first thing to do is risk assessment. You find a procedure and then start doing the risk assessment. So usually we don't encourage you to do risk assessment by yourself because you are doing something new, right? And therefore you cannot identify all the risk associated with it. So what you do, you want to talk to people. So it says here, make a risk assessment team. There is no such thing in the real world, right? In a research group, I don't think a bunch of you will come together and discuss your research, your experiment, right? But what you should do is you should talk to your supervisor, you talk to your seniors who have done similar reactions, or whoever is available, or maybe a postdoc who has more experience than you, and talk to that person and say, yes, I have to do this experiment, and I chat with you, or there is a procedure here, these are things involved, and how do I do it? Just to sit down, talk to that person, right? And then break down the process and procedure into multiple small steps. Don't think about just one step process. It's never a one step, right? So if you're doing an ester hydrolysis, of course it's a one step reaction, ester reacting with a strong base, it forms acid and alcohol, right? But then, when to do that, you have to first find the ester, you have to find the normal base. It can be sodium hydroxide, it can be potassium hydroxide, or some other, yeah? So then you need to find a solvent. Is it going to be ethanol? Is it going to be water? There are so many other concerns you need to do, right? So divide into smaller steps. And form a risk assessment team, gather relevant information. Relevant information means STS of all the chemical involved. Talk to the senior and get those people who have done this before, right? Their opinions. And divide each process into successive tasks. Yeah? Any experiment you do, you say the relevant glassware, the relevant solvent or chemicals, relevant STS, all these things you should accumulate, right? And then go through it step by step. Principal investigator, laboratory supervisor, or reporting on all are your professors, right? This professor should be the person who is suggesting the experiment. Or if you have an idea, you're most welcome to talk to him first. Yeah? It's kind of dangerous. There are many of you are much smarter than your professor. It's a given thing, right? You're much younger than him or her, and they have been working on the system, but they have a lot of experience. But then the way you think is different from your professor thinks, right? And you probably see a different angle of certain things than the professor thinks. So don't think that just because your professor says that you should blindly do those things, but you need to think about it, yeah, and then go and do it. So, but the suggestion usually comes from your professor. Why? Because he's in charge of your PhD program, right? And therefore he will say, okay, let's do this one, let's try this project, let's do this thing, right? Within that boundary, you can always do things by yourself. Yeah, you can bring in an idea, but always discuss with him before you jump in to do it, right? Because he or she may have more experience than you. Yeah. So when you suggest new ideas, he may say, oh yeah, this sounds interesting, or he may say, oh maybe these are problems associated with it, and he will highlight for you, yeah, etc. So do work closely with your supervisor. And then comes your lab members, let's say T-lead, etc. So for example, if you have a very reactive reagent or a toxic poisonous material, of course other neighbors should know, right? They say T-lead should know. Yeah? Don't do it in secret. And sometimes, we don't do it anymore. In the past, we used to make gold nanoparticle using thiol as a capping agent, and these thiols are really, really stinky. So what I usually encourage them to do is that don't do it when everybody is working in the lab, right? You open it either on a Saturday morning or evening when most of the people are left, then you're probably able to do this. Just that step, adding the capping agent to the nanoparticle solution, right? And so most people probably don't have to go through that stinky smell of thiols. Yeah, of course you have to do it because it's part of your research, right? But that doesn't mean that you have to put everybody through it. Yeah? So make sure you offer a little bit of consent to your neighbors, right? And then remember, you are never alone, right? We have a whole setup for safety issues, right? We have a department safety committee. Your supervisor is in charge, but department safety committee will always involve when there is a safety issue, right? And there's a coordinator who inspects the lab, etc., faculty safety unit, OSHE. There are many help you can get if it is something which is difficult to do. So information needed for a risk assessment to fill up that Excel form. I'll give you some examples. A laboratory layout plan, you don't have to draw your laboratory structure, etc. But layout plan, what it means is that do you have a few more to do this? Do you have space for you to do it, right? You must be aware of that. If you are not sure how your lab look like, you cannot do any experiments, right? So that's why first you need to go and get safety induction done by a safety lead. So he will tell you what to do, what not to do, yeah? So you need to be aware of that. And process flow chart is your reaction sequence, your project experiment sequence, what you want to do in the lab, right? List of work activities in the process. So what are the steps involved in the process? List of chemical equipment and machinery tools used. So what kind of glassware you need, what kind of heating system you need, what kind of other workup procedures you are you going to use a column, etc. All these things you should think all the way, not just setting up a reaction in the risk assessment. Risk assessment should be covering entire experiment, right? Starting from the end. Record a fast into safety data sheet and operation manuals you must have, right? For example, safety data sheet of all the chemicals you use. So if you want to do some other, I don't know, sonication or something like that, you need to know how to operate that particular instrument, right? Or you need to use ultracentrifuge, you need to know how to operate. You need to be trained before you start that thing, right? Don't jump in and say, oh yeah, I know how to use it. I have done this in my previous institution, but some of the machines are different. They may have different capabilities, even though they are from the same company, maybe an old version versus new versions, right? So you should always get trained by a senior, yeah, student in the lab. Records of past incident and accident. So when you talk to your seniors, they will say, oh yeah, when somebody did this, there was an incident, right? Somebody did that step, something went wrong. We had a broken glasses, we had an explosion, or we had a fire, we had this or that, etc., right? So that is experience you can gain from your own group mates, your own seniors, yeah? And those information is very useful before you do the experiment, right? So that those things come as a part of risk assessment. And relevant legislation, course of practice and specifications. So that also important. You do not need to go through those legislation, learn and blah, blah, blah. No. You need to know something about what kind of chemicals are used. Is it very toxic? Is it a poisonous? Is it explosive? How do you dispose those waste, etc., etc. Some information you should have. Yeah? Information needed for risk assessment again, observation, interviews, past inspection records, details of existing risk control, safe work practices, right? Those are already present, but you need to be highlighting that in your risk assessment. Previous risk assessment, if somebody has done the reaction. So as I mentioned, usually you are joining a project. It's very seldom you are doing something really, really new in a research group, especially when you start, right? You probably do something what other people have done. So you can actually use the previous risk assessment as well from your seniors. But do not just copy directly, right? That's another mistake many students make. They just change the name at the bottom and then submit. But that's not what you need to do. You need to go through it, make sure that all the steps are correct. This is what you're going to do. Sometimes, you know, the supervisor say, oh, you know, this person has used this chemical. Why don't you use this particular chemical, right? But then if you copy the same risk assessment, then when the supervisor need to sign, you will see the old one again highlighted in that particular risk assessment. So then you will know this is just a copy of that, right? Usually I tend to ask questions whether they understood or not, right? But many supervisors probably don't have that kind of time. And then feedback, you know, the feedback from your own group mates. Yeah, there are many resources available for you. All these are available in PDF form. You can find in the OSHI form or our department website. There is a safety link, and you can go and download those things and read those. Yeah, and that gives you more information as well. Okay, breakdown of process, as I said, input, laboratory workshop, activities, operation, output. So this is any reactions, right? You have some inputs are your starting material, etc. Output is your product, and then procedures, right? Hazardous materials, also when you talk about your starting material, there is a lot of consideration, right? You need your chemicals are really okay to handle, what kind of special consideration you need, etc. Am I using radioactive material? Then I need to have those kind of processes. Then many equipments are needed, right? Hot plate stirrer, roto evaporator, I don't know, distilling setup, all these kind of things. From the procedure itself, you know what kind of equipment you need. Yeah? And then sample collection, transportation. So, for example, sometimes you need to bring a solvent from the chem store to your lab, and how do you going to bring it? Where do you find those samples, etc. The reagents, right? Sample and chemical storage, personnel involved, etc. And then for the procedure, it's usually extraction, isolation, purification, manipulation, reaction, analysis, etc. Pilot plants, and then site work. Pilot plants and site work doesn't apply because you're not doing that kind of large scale. Sometime, you know, you probably scale up into a system, but this is relatively rare. Yeah, and then output is usually your product, waste storage, handling, and waste treatment and disposal. Because every reaction you do, you will have some solvent waste, some other waste as well. So you need to know how to dispose. Now, risk assessment is for the entire reaction. Risk assessment cannot be done half a little bit, and then you set up a reaction and come back to do the remaining one, how to purify compounds, those kind of things. No, you do it entire process until you get characterization done. Yeah? What kind of product you expect, etc. Because as I said, for every reaction you have an idea what you expect at the end. Yeah? You should have. If you do not know, then don't do that reaction. Yeah? So you have to do your risk assessment for the entire process. Distillation of dichloromethane, right? Very simple one, we know that. But you can, if you divide that into multiple steps, you will see how easy it is or how difficult it is. Some steps may be more tougher than the other ones, right? And that's where it helps you to identify the hazards involved in this whole process. If we just take it as a distillation of dichloromethane, you would not have identified all the hazards associated with it, right? So that's why it is broken into multiple steps. Dry all glassware, set up distillation apparatus, clamp the round bottom flask, connect solvent, collector, condenser. These are different instruments involved, right? Glassware is involved. And then what can go wrong in this whole process? In the first process, it's just setting up the distillation setup, right? What can go wrong? Usually, because these are all glasswares, right? So when you are using those, you can break and give you cut in your hand. Sometimes when you are drying the glassware, you have to put in the oven, and it's usually higher temperature than the other one. So you make it, if you go and touch the hot stuff, you will get burns and things like that, right? So all these kind of things should come in your head when you are doing the thinking about that particular stuff. Yeah? And that's what we look at the hazards and risks. To the round bottom flask, add air-grade dichloromethane, 2/3 of the flask. Yeah? What can go wrong in that step? when you're adding dichloromethane into that flask? Of course, it's a spillage, right? Because you're adding from a maybe 4-liter bottle to the small 1-liter flask or something, right? So spillage is the main thing. And what could be the accident associated with spill? It is falling on you, getting exposed to the chemicals on the skin, blah, blah, blah. And then you need to find a control measures how to prevent that from happening. So the solution, 10 gram of calcium hydride to the flask. Again, calcium hydride is the drying agent. We usually use it for DCM, for example, right? Then you can think about calcium hydride is a reactive metal hydride, relatively less reactive than sodium hydride, but still it can react. So there should not be any water around. Chances of this falling into water or aqueous containing one will be very reactive, right? So you need to identify those. And then after adding the required calcium hydride, turn on the water circulation heating mantle, right? So heating has to be there as well as, because you have to reflux in the DCM before you can dry it. Yeah? And then the condenser should be set up. So here we have the condenser already, right? So water should be on, otherwise all the DCM will evaporate from the plasma. Reflux dichloromethane for 2-3 hours. And again, there you want to make sure that it is done safely, what other things can go wrong, bubbling over and blah, 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 right? All those things we need to consider. Correct desired amount of dried dichloromethane into another flask for you to use it, right? Turn off the heating mantle, cooling the setup, and then refill the round bottom flask with the dichloromethane again if you want to use it. Dispose of the waste chemicals and containers, etc. So these are full distillation process, right? Up until the disposing the used material or whatever is left over. So all these steps have different risk associated with it. That's what you will need to think about and come into practice. So for my team, gather information, etc. Again, team is not, don't go and ask for 5 people in the group and say, oh, I need to distill the DCM and can you help? Usually they do help, maybe you need another person, etc., right? But what is the important thing is discuss about it. There may be a senior who has done it. He or she may help you to set it up, the system, or say that, oh, don't do this, but do this way, etc., right? What should be included in the chemical risk assessment? All these things should be included. Yeah, not just half of the stuff, but entire process should be included. Person at risk, person directly involved in the experiment, of course that's you, or operation. Person not directly involved in the experimental operation, who are those people? Your neighbors. You know, the person who is working just adjacent to your fume room, right? And they can also be dragged into this whole process if there is an explosion, right? So you need to be aware of that. Unless you are the only person working in that lab, which is very unlikely, right? You have multiple people in the lab. Visitors not allowed in the lab, yeah? So make sure that nobody comes to the lab. If you have friends visiting you, meet them in the student room, right? Not take them into the lab. Yeah? Members of public, how the members of public will get exposed to your reaction? Do they get exposed? Members of public usually mean that, you know, the group, not your group member, but it can be other group members, you know, in the same floor, or if you're taking to the store, the people working in the store, all are members of public, right? They have no knowledge of what you do, yeah? So they will come into picture when you're taking waste to the store or something which you're taking out of your lab, right? And that, or if you're throwing your organic waste into the sink, of course it will affect the members of public as well, because you remember in Singapore we recycle water, right? All these drainage will be collected and recycled later on, right? Involve all student lab techs, process, research, etc. So as I mentioned, if, especially based on the hazards, you can identify, let other people know what you are doing, right? And don't do it in secret. So again, reflects dichloromethane, and you can see different hazards associated. I mean, this is only one step here, but you should split them into multiple steps, right? Like the previous one, as I showed you earlier, right? This is the different steps involved. So instead of just writing one step, I would write all these 10 steps here, and then look at their hazards, and then identify the possible accident, what can go wrong, etc. Right? And that's how you decide the next step. And then another one, laser alignment. Laser is another experiment some people will work with. So you need to see turn on the glass laser, class 4 laser system, perform alignment work, turn on class 4, turn off, right? And these are, again, the hazards associated with each step is different. Yeah? You can get an electric shock if you are going to turn the switch, permanent eye damage if you look directly into the laser, right? Skin sustained laser burn, if you put your hand in the laser beam, you can get skin abrasion and things like that, right? Open wires, and when you're touching any switch, you must be very careful, right? Electrical shock would be the common one. Then the other one is DNA extraction from human cells. Again, that's more like a biological experiment, right? Many of you probably don't do it, but again, split into different steps, and then look at the hazards associated with each step, yeah? And then do the what can go wrong, possible accidents, right? So go through those steps and understand how these divided, and more steps you create, the easier it becomes, yeah? Instead of one step process, right? So that each step you can identify what are the hazards involved. This is even more exotic, like electrospinning. I don't think we are doing. We used to do it in the old days, but now we go to another lab and do it. But other labs in chemistry are not doing at the moment, as far as I know. So it is a kind of making nanofibers based on high potential, right? Polymer solution, etc. So you can see they have split it into making the preparation of solution, and then grind the tip of the needle in order to collect the fiber, etc. Set the parameter, pour solution into a syringe and connect to the circuit, switch on the high voltage, spinning the fiber, stop spinning, collect, and these are different steps involved, right? And each one of them may have multiple hazards, and that's what you need to identify under the hazard column. This is an Excel file, right? Here you are only shown the first 3 columns, but there are many other columns you will see. Later on, the 4th one will be something, and what kind of control measures you have, etc., etc. And so once you identify hazards, then you can think about what accidents can happen. So risk evaluation, existing controls and risk evaluation associated with it, identifying the existing control measures, assessing the potential severity and the likelihood. Remember, in the last class I also mentioned that, right? Risk is a multiplication of severity versus likelihood. So we give some numbers and then see how bad that is, yeah, determining the risk. So in a general rule is that if the risk is 3 or above, or 4 or above, then you should not be doing that reaction. You should have additional control, etc. Right? Anyway, we will come to that chapter. Existing control measures, what do you already have practiced or implemented in the lab? So usually all the reaction you do are relatively safe. Yeah? There will be sufficient control in the lab to handle the hazard. Right? Dilution of sample, restricted quantity to use. As I said earlier, never do the large scale reaction in the first time. You always do it in a small scale and then scale it down. In the first time, when you do small scale, all the hazards are minimized. Yeah? Because if something goes wrong, if there is a fire, then you have a very small fire as compared to a large scale fire, right? So you can handle those things. And you will learn a lot by doing the small scale reactions. You get an experience with how to handle those things. Teamworks and biosafety cabinets, interlock in the system, alarms, etc., training and communication, standard operating procedures, food entering in the laboratory, personal PPEs, etc. All these are already in place. Yeah? So you can actually use them as a control measure to control the hazards. So here is the severity and likelihood. I think we talked about this earlier. So hazard is divided into the how severe the hazard is, and then how often this can happen. Yeah? Then you look at the multiplication, right? Severity and likelihood, and then just give some multiplication of these two numbers. So, for example, when you look at this, severity, minor, no injury or ill health required for first aid treatment only. So, if it is just a cut, it's not very severe, right? The cut on a finger, you can just put a band-aid and that's probably done, right? Or wash it properly with the water and put a band-aid and go to hospital and show the doctor, that's it. Nothing major happens. But if the cut is very deep, a lot of blood is coming out, then its severity is very high, right? Then you cannot say it's a minor. It could be major in that sense. So it depends on what kind of things we are talking about. This can go from 1 to 3. Yeah? 3 is the highest, and then 1 is the lowest. Yeah? The major is usually fatal. Fatal means it's really life-threatening. And then serious injury of life-threatening, occupational disease, amputations, etc., etc. Right? In between the minor and major, of course, you have moderate, right? Injury requiring medical treatment, or you have leading to disability, things like that. So moderate and major are much more serious. Minor is not so much. So most things what you do in the lab should be in the minor category, right? When it comes to moderate and major, you should start thinking about what additional control do I need to prevent these kind of things happening, right? So if it is a major one, try to go through the risk control measures, elimination, substitution, engineering control, administrative control, etc. to reduce that risk to minor. Yeah? So sometimes we should be able to do it, sometimes we may not. So these are things you need to make a decision when you are doing the risk assessment. The severity will not change unless there is a physical change of the equipment or process. So for example, as I mentioned earlier, lithium aluminum hydride, it is flammable, guaranteed, right? So you cannot change the nature of lithium aluminum hydride, whether you use small scale or a big scale. But what can you change then? You can change the likelihood of fire. How? You use a smaller amount, or use a paraffin coated lithium aluminum hydride than a dry powder. Yeah? Those are kind of things you can do it to reduce the likelihood of those. But severity, the fire is still there. Yeah? So that's what you can play around. So again, likelihood is remote. For example, if things are, as I mentioned just now, if you use a powdered 99% pure lithium aluminum hydride, it's guaranteed to get flame because humidity in Singapore is very high. Now it's a little bit better because all labs are air conditioned. You know, 10 years ago, some of the labs were not air conditioned, so you really have to open in the air, right? With air conditioning, the humidity goes down, right? You know that, right? Air conditioning, part of it is a dehydration, dehumidification of the air, right? So you have a less amount of moisture in the air, right? So it is, you can say if I'm using very like 100 milligram, the severity is still high, it can catch fire if it's 99%, but likelihood of catching the fire is small because I'm using very small amount, right? Or you say I'm going to use 60% with paraffin coated lithium aluminum hydride, that's zero. Then likelihood of fire is almost zero. It becomes a remote chance. Occasional or frequent. Frequent would be, it is guaranteed it's going to happen. Then that's when you go to the elimination, trying to not to do that process. Yeah? But occasional, maybe you can still do it, but with an additional control. Yeah? So how do we get all this information? Again, STS will be a good one to look. Past experience and incident in the lab when somebody else used it and how it went. Complexity of the activity, so how complex the reactions are, how much material is involved, how many materials are involved, etc., etc. If the lab is full of people, you're kind of squeezed into 3 people working in the lab. That's a complex environment as well, right? Or if you are doing a large scale, that's again a complex environment. So if you're in a normal sense, the complexity may not be that high. So number of personnel involved in the activity, again, if you are doing alone, then it probably has a factor, right, as compared to multiple people working together. Risk is equal to severity times likelihood, right? So if you have it can reduce your severity and likelihood into more, acceptable level. It should be low, right? So for example, minor, moderate severity in this case, and then likelihood is on this side. So if I have a severity is minor and remote chances of happening, then it's basically 1 to 1. 1 times 1 is 1, right? The EC, you can go ahead and do it. So when you have a likelihood is 2 or 3 and the severity is minor, then again you can go ahead and do it. So when you have a green color, like 2 or 1, no problem, you can do the reaction without any additional controls or anything else. But still you need to do risk assessment, take all the precautions, etc., right? But they are relatively safe as compared. Even the more medium ones are kind of safe, but you should not go ahead and do like this one, right? The minor one. You should have extra precaution. Somebody else should be aware of what you're doing. Some additional control should be there. If a fire breaks out, what am I going to do? Do I know the fire extinguisher where it is, or do I have a mechanism to put it off? All those things you need to think about when you use the medium. Okay, medium is 3 or 4, right? And then anything above 3 or 4, you should not do it. Period. Yeah, you should always find some way to bring that score to either 3 or below. Then you can go ahead and. Now bringing score down to is not a difficult thing. That's what I'm saying. You need to go through the process again and see how to change it. So for example, if I am going to, first time I'm doing it, I'm going to do it in a 1 liter scale. That is already the high risk because the play. So how do I bring it down? I do it in a 10 ml scale. Then I can actually bring the score down, right? So if I am using lithium aluminum hydride, which is extremely flammable, either I use a 60%, then I can bring it down again. Okay, I use a very small amount, bring it down. So there are many steps you can do. Or I replace the lithium aluminum hydride with the sodium borohydride, which is much milder. Then I can do that. Or do another reducing NaCl or something else, right? Again, these are things you can make a decision because you are the one who knows the reaction well, right? And you can do a literature search and see is there an alternative process I can use, which is much more safer than what I'm thinking of, right? So these are, you have a question there? Okay. I thought you wanted to ask some questions. So, okay, so look at these kind of numbers, right? And if it is larger, then you should not do it. Yeah? Low, you can go ahead and do it by yourself, no big deal. But when it comes to medium, always get some additional control to make sure this runs smooth. Yeah? Determine severity, etc., no injury, blah, 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 minor. This one we already talked about, likelihood, etc., right? And then you always look at this green level. Yeah? Different people have, in NUS, we can look at 3 by 3. The 9 is the top most score. Some industries actually use a 5 by 5, the 5 type of categories, right? Again, it's the same principle, but they have additional, items under this, and not just minor, moderate, and high risk, right? They will say maybe minor and I don't know what other category they use. So in NUS we use this kind of 3 by 3 format. Okay, so entire risk assessment will look something like this, right? So these were the one we were talking about earlier. And then step 2, the control measures we put in is the 4th column, and then risk severity is the next one, likelihood is another one, and then you do the entire risk level. Yeah, this is a multiplication of these two. Yeah, so when you have the 2 times 1, you will get 2, right? When you have a 2 times 2 is a 4, right? Like that, right? And then if it is 5 or 6, then you should not be doing that step. You should try to eliminate. Yeah? The lower one is fine. Now, many cases, what the students usually do, again, these will be picked up by auditors, right? Then they go through your risk assessment. Everybody don't want to put anything above high. So every step they talk about is always 1 and 2. But that's not true, right? You need to look at the stuff carefully and then assign. Okay? Don't just put random numbers like 1 or 2, irrespective of what you're going to do, right? Then it looks like all small numbers. So these numbers should correlate with your steps, what you're going to follow. Yeah? And correlate definitely with the hazards associated with it, right? If there is a fire hazard, then definitely severity will be high. Yeah? If it is something else, because the lab had many other incidents, then likelihood will be high. Yeah? So these are things you really have to think about and do the number, not just randomly put 1 or 2, and then you get into trouble. Okay? So again, remember, risk assessment is you are doing it for what? Not just a procedure, right? It is actually for you to analyze the risk associated with that particular experiment. So now if you put 1 and 2, and if you do that process and get into danger, so what will happen? You will get into big trouble with our the safety auditing team, right? They will say, oh, you are not serious, you did not understand how to do the risk assessment. Then you should have talked to the safety lead or a professor to do it properly, right? So that's what you must avoid, because if you do it properly, then even if something goes wrong, you are protected. They will not blame you, right? But if you do something really not very well, you fill up these things and give it to them, then of course there will be a problem, right? So please pay attention and do it properly. Yeah? And if you are not so sure, ask help. You don't have to always do everything by yourself. There is always help provided. Now, again, as I mentioned, when I say help, you can either go to safety lead, and if he or she is not cooperative, then go to a professor, and if he or she is very busy, then where you go? You go to department safety officer, right? He will definitely help you, because that's something. But he will not do risk assessment for every reaction you're going to do, right? He has better things to do. But he will show you how to do it. He will actually explain to you, just like what we are doing right now, right? He will explain to you, etc. And then you need to learn and do it. Yeah? It's not very complicated. It just takes some time for you to think about your experiment. And that's the purpose of risk assessment. You need to assess and analyze the details. So again, there are a few of those things, and you can see the numbers, how come in. So some we have a 3, some we have 2, etc. So therefore we can actually go ahead and do it, right? If the numbers are 5 or 6, absolutely we need to avoid that, right? We should not do that stuff. Same thing, laser element, most of them are okay to do, right? 3 or 2 amazing. So when it's facing the eye, then it becomes higher, right? You see the severity, because you can get eye damage if it directly come into there. But likelihood of that happening is relatively low. Why? Because we are trained to not to look directly into the laser, right? So very seldom it happens. Very seldom doesn't mean that it doesn't happen. In fact, we had an incident where a student directly looked into the laser, yeah, and then she had a problem with her eyes, etc. So this can happen, but usually it doesn't happen. Why? Because you are trained to not to look directly into them, right? The electrospinning, again, look at those things, how you put in there. So these are exercises you can try to understand, and I would love you to actually read and go through it, right? If any problem, you come and see me, I can explain to you why we give this number or not the other number. These are numbers given based on the hazards associated with, based on the accidents and possible health issues associated with, right? So you need to make sure we justify what numbers we give. Yeah? Don't give random numbers, that's what I'm trying to say. Because auditors are specifically going to look at those, yeah? Because they are, I have seen this many times with students doing it. So you should be able to explain why you give that. Risk control. So we need to manage the risk where we look at additional controls. If numbers go 3 or anything above, then you need to have some additional controls in place so that it doesn't get out of your hand, right? And then we say responsibility or compliance, who will help you? Because you yourself may not be able to do it. Somebody needs to be even included in the responsibility. And then communication and record keeping. All those things have to be written down. Now, this is a chunky airport. You probably know that, right? We parked along in, I think it's a Terminal 3. Yeah? Now, imagine you're actually flying, right? Usually, I'm sure every one of you have taken a flight, right? Because either you came from your country to here, or if you are Singaporean, you're gone for holidays and things like that, right? Can you imagine the flight is made with what? The plane is made with what? Do you know? Aluminum. Yeah, it's not as good as a steel, right? Aluminum can be easily bent. You know that, right? Because aluminum, you can actually, it's a soft metal. And how many passengers usually go with a flight? Like a A380, how many passengers? A380 is a double-decker one, right? And how many people can sit in that? Usually 500 or plus. Some actually go up to 600, depends on the seating arrangement. Usually for like Singaporean airline, maybe 520 or something like that seating. Yeah. So you can imagine the 500 people sitting in this aluminum can. At what height usually they fly? What height usually they fly? Come on, you guys never been to the flight? It's 30,000 or above. Yeah? Why do they fly so high? Do you know? Why do the flight actually go very high up? They can still fly low level, right? They're safe to fly in a low level, but usually they fly very high up. Why?
Good.
Is what? Avoid what?
Things in the air that are
No, there is nothing. I mean, when you take off and landing, you still have to come down, right?
Because the weathers,
what?
the weather in the stratosphere.
It's not weather. Weather can be money. Pressure. Yeah, 30,000 or above. If they don't fly below. Okay, but why is that? There's a purpose. That's why they do it. And they cannot go 60,000, right? They cannot go very high also, because then there's not enough air. When you go up, the height, the air density decreases, right? The air density at the bottom, closer to land is much higher. So when you fly in that, it's like, when you have a low density air, the friction is very less. Therefore, the energy you need to spend is much less. Yeah? So higher the altitude it flies, more safe, they can save more energy, more fuel. Yeah? So if some newer technology, they can go up to 40,000. Some of the new, like A350 for example, they can fly like 38,000, 40,000, right? So they can manage that. But because of this energy saving concept, that's why they fly all the way up. But can you imagine 500 people in a tin can at 30,000 feet up? In a car, or if something goes wrong, you can stop at near the side, side of the road and open the door and come out, right? But in the flight, you cannot. What are you going to do? If you open the door, you immediately die. because the outside pressure is much lower, right, than inside. But yet there are millions of people traveling on a daily basis all over the world, right? So why do the people do it? So if you think about the severity and likelihood, at 30,000 feet, 500 people in the cabin, severity can be very high. If even a small hole will cause problems. Yeah, that's why you're not allowed to carry gun in the flight, right? Because if somebody shoots, it will go through the aluminum very easily. Yeah, even the safety officer are not allowed to carry the gun. Yeah? But then if you multiply severity and likelihood, what kind of number can you get? Can it be 6 or can it be 5? Can it be 4? That's how you look at it. Is this practical? And it's practical. And it's allowed. It's legal, right? Because there are a lot of regulations they have to pass through before they can fly. Yeah. So, and they are not. This is not only for luxury travel, right? It's not like 100 people traveling a day. We have millions of people take flights. Yeah. So that is where you really have to think about how what can happen in the air when you are up there. It can be very severe. If there is a small hole, you'll die immediately. We call implosion, right? Severity, pretty bad. Yeah. And then why are we still taking flights? Likelihood, probably. If something goes wrong, you really have a pretty bad problem in your hand, right? But if you look at the statistics, we don't have so many accidents in the airplane industry, right? Only few happens once in a year, once or twice a year. Yeah, depends on conditions. So in the earlier 1930s, there were some incidents. 2000, it's become lesser and lesser, right? So odds of being involved in a fatal accident, 1 in 5 million kind of thing, right? 1 in something like that. So the number of incidents are very low because of the safety precautions, right? So likelihood will be very small number. Even though severity is higher, likelihood will be, so severity could be 3, but likelihood is 1, right? So 1 times 3 would be still okay. But there is hazards. It's not that we have completely eliminated, right? The things can still go wrong. That's why we have some accidents during this event, right? So identify reasonably practicable measures. So that is also very important. So reasonably practicable measures are the one which airline industry goes through, right? Because they know there are problems, but then as a practical approach, they can be safe to fly because they have all the control measures in place. They go through the strict maintenance of the engines and things like that, etc. Right? Implement the control measures all in place. In fact, each country has its own regulation and they have to follow those things. Based on the risk level, select additional risk control measures to reduce the risk level, right? So some airlines will have certain restrictions and other airlines, right? So they will use that. Review continually to ensure their effectiveness. So all these measures. So what is reasonably practical? An action is considered to be practicable when it is capable of being done. So it has to be practical to do things. Yeah, we cannot insist that all of you wear, the complete suit, go to the chemistry lab, right? It's not practical because it is very inconvenient and we do not need that kind of safety, right? So that's why we only ask you to wear PPEs which are reasonable and practical. That means a lab coat and goggles and the closed shoes, right? So that is very important. We do not ask you to wear the full suit which people wear in the biological, class 4 lab and things like that. Safety, whether it is also reasonable, takes into account safety of injury, harm if you have, degree of risk involved, and knowledge of hazard and the ways of eliminating and reducing, controlling it, and then availability, suitability, cost of safe harm. So whatever things you need to analyze the entire process and then make the decision. Yeah. Now you as a consumer, you can say, I don't want to fly. There are a lot of people who don't want to fly. They stay at home, right? Or they take if you're in US, they will drive, right? If you're in other countries also, you can drive from one place to the other. But going international is difficult, right? But now I think they can still drive from one country to the other country. It takes a longer time, that's all. But there are people who don't fly because they are afraid of that. But in general, it's safe to do. Same thing goes for your reactions, right? You have to do reaction. You cannot say all the safety talk is not to prevent you from doing PhD, right? We say you do it safely. That's what's important, right? You can carry out reaction, you can carry out research in a safe manner so that you yourself will not get into trouble or the institution don't get into trouble. Yeah? So that's one of the practical reasons. So we do it in a reasonably practical measures. Yeah. Let's take a 10 minutes break and come back. Yeah?